Now I'd like to invite our last speaker, Benoit Tremblay, talking about the Sun as a fully developed star. This will be an online talk as well. Let's see if we can get this up now. Great.
Hello.
Hi. It's been great. We see your slides, so you can start, and I'll give you a warning in 15 minutes, okay?
Okay, perfect. Thank you. So hello, everyone. In this presentation, we want to highlight how we can use existing satellite missions as well as deep learning to try to measure the sun's emission from any point in the solar system. To give a bit of background, this project was designed for the 2022 edition of the Frontier Development Lab. And it was tackled by a team that you're seeing on the right. I want to point out that while I'm presenting virtually, Robert Yerlim, one of the researchers on the team, is participating in the meeting in person. So if you would like to learn more about the project afterwards, do try to find him. All right, so let's start. The project was designed and motivated by multiple science objectives, including measuring the impact of the sun's UV radiation on Earth and our assets in space, measuring its impacts on other planets in the solar system, and then generalizing knowledge of the Sun-Earth system to other O stars and their exoplanets. It was also motivated by trying to improve our understanding of the sun's dynamics, as well as trying to connect to other stars in the universe, with the sun being basically the template that we can use to study them, but they might have unknown inclinations and things like that to make it challenging to generalize. But when it comes to the sun and EUV, we have a limited number of EUV observing instruments, and they've mainly been constrained to viewing the sun from the ecliptic plane. So basically we get an ecliptic view. Latitudes typically range from like -7 to 7 degrees. We have the SDO satellite that produces images of the sun in UV from Earth's perspective. And then we have the stereo twin satellites, which provide 2 additional viewpoints, with the stereo B satellite falling behind Earth's orbit and the stereo A satellite moving ahead of Earth's orbit. However, a complete image of the full 3D sun is kind of necessary to really fully understand its dynamics if we want to forecast its activity as well as to relate to other stars and other planets. So that brings us to the main question of our FDL project, which was how can we observe the sun from any perspective? A solution to this would be to just launch more satellites. But the solution we propose here is to add virtual instruments using machine learning. So these virtual instruments can be placed in ecliptic orbits, as well as in non-ecliptic orbits at any time around the sun, providing us with completely novel perspectives of our star. For this, we're going to try basically to leverage the multi-viewpoint satellite data that we have available to try to generate then a 3D model of the solar atmosphere, as well as trying to account for temporal evolution. And then once we have that model, we can then generate novel perspectives as if we had a satellite placed at a given position around the sun. And to achieve this, we're using methods known as neural radiance fields, which are neural networks that learn from a limited number of images taken from different viewpoints, and that achieve state-of-the-art 3D scene representation. NeRFs were originally designed to generate 3D models of static and optically thick objects, which is definitely not the sun. So the sun's atmosphere is dynamic, it has complex geometries, and it's filled with plasma that's optically thin, which means that it can absorb and emit light. So therefore, we had to adapt neural radiance fields to more accurately represent the physical properties of the sun. So for example, rather than modeling something like reflection, our NeRFs model for the sun will model emission and absorption of light from the corona. And then once we have that model, again, we generate novel perspectives of the sun. So we'll dive a bit more into the method. We call our new model SuNeRFs, or Sun Neural Radiance Fields. And we have a plot on the right that kind of illustrates the principle. So basically, let's start with from our satellite. It captures an image of the sun. Basically, we are going to create a model, a 3D model of the sun's atmosphere within a box. And the way neural radiance fields work is you start a light ray from the satellite you make it go through a pixel of the image and travel all the way inside the 3D, inside the volume that we have for our sun. And then inside a volume, along the light ray, we're going to sample different points. And basically for each of those sample points, we define a position and a time. And once we define those, each position and time will be provided to a neural network, which is just a fully connected neural network. We forepass it through, and basically the neural network is going to output air emission coefficients and absorption coefficients at each of the points along the light ray. Once we have that, we're going to integrate along the light ray all of that information. Basically, it's a form of very basic radiative transfer in a sense, or a way of trying to incorporate some physics in the model. And then from that, we're going to try to recover a 2D image. And then we can compare that 2D image that we inferred with the 2D image that the satellite produced. This is how we optimize the neural network, essentially. It's comparing the 2D images that we can generate with the 2D images that the satellite observed. Now, we do this not just for one satellite. We do this for all different satellites that are available around the sun, and we do it for multiple times. Basically, we're trying to take advantage of the sun's rotation and evolution over time to provide us with additional viewpoints in a sense. I want to specify, though, that this model is only valid for the time sequence that's covered by the observations used for training. Don't expect this to be a forecasting tool. This is just, here's a sequence of 2D images, and let's try to make a 3D model of the sun plus time for that time sequence. Next, let's move on to try and validate this method. So we want to use ideally a data set that has a ground truth. So for this, we use a simulation of the sun's atmosphere in EUV that was developed by Predictive Science Incorporated. There's a total of 256 viewpoints that are available for 3 of SDOAI's wavelengths. Basically, what we did was, in order to match the physical reality of existing satellites, we trained a neural network using only viewpoints close to the sun's equator, which are represented in magenta on the left plot. And we use the remaining viewpoints as test data, which are represented in green on the left plot. So here's a side-by-side comparison between the ground truth, which is the simulation, which is shown in the first row, and our SuNeRFs rendered images, which are shown in the second row. As we move from left to right, we're showing the transition from ecliptic viewpoints, so less than 7 degrees, which were part of the model's training, to the novel viewpoints at higher latitudes, including all the way to the pole. So what we're seeing is that the SuNeRFs method provides reconstructions that are consistent with the 3D geometry of the simulation. And in particular, it can recover information from the simulation's polar region, despite learning only from ecliptic viewpoints. So I think that's one of the very interesting features, is inferring non-ecliptic viewpoints just from learning from ecliptic images. The third row shows the primary difference between the reconstruction and the ground truth. And we see that the larger differences typically occur close to the solar limb and at the more complex active region. And finally, in the last row at the very bottom, we're showing the model's uncertainty, which we're estimating by training an ensemble of models with different initial conditions and then computing the variation between the individual results. And note that the uncertainty maps and the difference maps have a pretty strong spatial correlation. So that's one way of evaluating. Another approach that we use for evaluation, for example, is just to look at performance as a function of longitude and latitude. So for both of those plots, the different points that you're seeing represent the 256 viewpoints that were from the simulation data. The red dashed lines indicate plus and minus 7 degrees, which was basically the range used for the training data. So basically anything between the 2 red lines were part of the training set. And the metrics that we're focusing on here is the peak signal to noise ratio. So the higher the value, the better. And the structural similarity index measure on the right. So you want a value ideally close to 1. So kind of as we expect, close to the ecliptic, this shows the best performance because that was part of our training data. But as we move to non-ecliptic views, we only see a marginal drop in performance for higher latitudes, which is pretty encouraging in the context of trying to apply this to observations. It sounds like it might be possible to recover non-ecliptic viewpoints despite learning from only ecliptic viewpoints. So on the topic of observations, let's now train another model. So we trained from scratch, but this time using real observational data. And specifically, we use EUV images that were captured by SDO AIA at those 4 wavelengths that you're seeing. And to add more viewpoints, we're also using EUV images from the Stereo A and Stereo B satellites that have slightly different orbits. So while SDO and Stereo observe the sun largely in the same spectral bands, they do have some differences. And so to have a more homogeneous data set, we're using a method called instrument-to-instrument translation. Basically just so that the images look similar. That way, it's a good requirement in terms of combining the observations into a single representation. And if you want to learn more about the method, you can ask Robert at the meeting. So again, just the perspective of what we're trying to do here, we're going to try to do a 3D model using a sequence of 15 days taken from 2014, where we had the maximum separation angle between the different satellites to get a maximum coverage of the solar atmosphere. So this is an example. With only 3 different viewpoints, we fully recovered the geometry of solar features and create observations at arbitrary viewpoints. And while the original observations are obtained from single ecliptic orbit, we can now reconstruct arbitrary viewpoints, view solar eruptions from all angles, and can even account for temporal evolution. With this, our method provides observations that would otherwise require normally multiple satellite missions. It allows us also to get unprecedented view of the sun. We have examples of SDO and stereo images on the left, but in the middle, we're showing what is arguably a first complete image of the sun's south pole in different wavelengths as well, as you're seeing on the right. So the arrows in the middle plot indicate the viewpoints around the sun that we use for the reconstruction. The big arrows correspond to the images that are showing on the left, where we can just barely see the polar regions. And as we can see from the middle, the method that we're using enables a consistent observation of the solar south pole, where we can clearly determine the boundary of the coronal hole, which is indicated by the red dashed line. This would be challenging to do from ecliptic viewpoints. For example, as shown by the blue dashed line, which is a reprojection of the coronal boundaries that we would detect in the images on the left. So this is really relevant for long-term study of the evolution of the sun and to improve our understanding of the polar coronal regions. Speaking of coronal holes, another interesting thing that we can do with this is exploit the 3D geometry of our model to learn more about solar features. So on the very left, you're seeing a stereo observation, and here we're fixing a longitude as shown in red. And along that longitude, we come across a coronal hole and a filament. Using our SuNeRFs model, we are going to render a new observation, which is the same thing, except that red line is now seen from basically on the right side. And with our 3D geometry, we can then look at the emission above that red line, which is what's shown in the slice in the middle. If we integrate radially that emission, you get the profile on the right. And what's interesting to see is that, for example, we're seeing a peak in the emission profile right above the active region. And then as we move to the coronal hole, we see a pretty significant dip in emission. And same thing, we see a bit of a dip in emission for the filament. When it comes to coronal holes, this could be an interesting way of detecting their boundaries, because we're really seeing a significant change in the emission profile, both for the coronal hole here as well as for the polar coronal hole at the bottom. Next, we don't have to just focus on a global view of the sun. We can also look at more confined regions. Specifically, like in this case, we're looking at a 3D reconstruction of a solar eruption that was captured by SDO and stereo. The image on the left is showing you the emission that our model is reconstructing based on satellite images. We see a filament that becomes unstable and erupts, leading to a coronal mass ejection. The central frame is showing you height information that we can estimate as a distance from the solar center. So that's taken from our model, taking advantage of the 3D aspect. And it can also track this way the rise and eruption of the filament. And the flare ribbons are mapped close to the solar surface as well, which is in agreement with our physical understanding. On the right, we're also seeing absorption, which shows the distribution of that plasma, which is rapidly ejected during the event. For sake of time, I'll go very quickly on this slide, just showing that if we take that model, we can then make like a side view of the eruption, which can be interesting in terms of trying to learn more information about what's happening in there. So to recap, SuNeRFs can view the sun from completely novel perspectives beyond what any existing satellites have achieved until now. So using AI, we enhance the existing observational capabilities of satellite. And now we have a virtual instrument that can fly out of the ecliptic plane and fly anywhere in the solar system. For example, in this video, we have our virtual instrument that is traveling from planet to planet, providing us with new perspectives of our closest star. And it can do so in multiple wavelengths. So to summarize, we use multi-viewpoint satellite data to generate a 3D model of the solar atmosphere that also accounts for temporal evolution, and then from which we can generate novel perspectives. This is interesting because it allows us to see some things like, for example, the poles. But this 3D model can also be useful for other things like detecting coronal hole boundaries, tracking solar eruptions, as well as estimating spectral irradiance from EUV images, which was also part of our FDL project. So you can ask Robert a bit more about this part. And we also have a prototype at the moment where we're trying to estimate density and temperature as outputs rather than absorption and emission coefficients, which allows us to account for the different wavelengths available as well as the response functions from the instruments. And then finally, having those novel perspectives can help us inform future constellation or cluster missions. Thank you for your attention.
Great, thanks for a very interesting talk. Do we have any questions from the audience? Yeah, we have one.
Hey, that was wild, really cool, thank you. Do you mind going back to the plot with the longitude, latitude, and error stuff on it?
Yes. Is it the one with all the dots?
Yes, yeah.
Okay,
yeah, here.
go.
Maybe it's just me, but on the SSIM, I think there's some sort of periodicity across longitude. The sort of orangey things peak around maybe 100 degrees longitude, 50 degrees latitude, and then maybe every 100 degrees longitude after that. I don't know if you can see that. I'm colorblind, so that also doesn't help. But is that something I should be worried about, or you should be worried about?
Yeah, it's not something that I noticed. Yeah, I don't think we ever noticed this. Should we be worried about this? I don't know. We should probably revisit this just in case, but yeah, I don't have an answer for this.
It's a very ill-posed question as well, sorry. Really cool talk though, thanks.
Thank you.
The best kind of questions with no answers. Any other questions from the audience in here? I think Cameron.
Thank you, very cool presentation. So you validate against an MHD simulation, but I mean, how confident are you that the simulation itself is correct? And that's one of my questions, especially when you get out of the ecliptic, right? And then you were talking about height in one of your last slides. And what does that mean? Can you define the height of the features? How do you define the height of the features?
Right.
If
so
they're
for
not
that first
exactly
point,
optically thick, right?
right. So for that first point, yes, of course there's the whole question of how realistic is the simulation. In this case, we use the simulation because it's what's available in terms of having a ground truth for something that would be non-ecliptic. When compared to the sun, that's a whole ordeal in itself, doing this sort of comparison. So we didn't do any of that in terms of how reliable or how trustworthy is that simulation. This one was, it was generated as part of an eclipse that happened a few years ago. But yeah, I would have to refer to the papers that I think I put on the slide here to learn more about the details for this one. It is just a case of, we don't have non-ecliptic viewpoints that we could use for validation, so let's use a simulation where that's available.
Okay. Well, probably will soon.
Yeah, I mean, we can talk about solar orbiter, for example. We do have examples of this doing this, but for the time sequence that we're focusing on, it was mostly ecliptic.
Okay, thank you. And yeah, I guess the second question was about the height of the
heights.
features, and then on this slide in particular, maybe I missed this, but how far does your model extend radially?
Yeah, so the model extends to 1.3 solar radii. And basically, because this is a box and we can estimate, for example, an emission and absorption coefficient at every point in there, that's basically, in a way, what we can mean by height information is that the distance, for example, from the solar surface where we estimate those coefficients is where you can access that information. So, for example, that plot that you're seeing in the middle is showing you the emission as part of a slice that spans from the solar surface, so 1 solar radii, all the way to 1.3. And you have access to information about the emission at each of those points.
Okay, so just a comment. You know, it could be very interesting to, you mentioned that you were working on density estimations.
Yep.
So, you know, you could think the next step could be, you know, trying to compare to in situ observations and see where these streams are coming from when you measure them with Parker Solar Probe, for example.
Right,
Yeah.
that's a good idea. Thank you.
Great. Any other questions from the audience here? Nope. Let's go to online.
Yeah. Okay. Oh, go ahead. Okay, I'll go. Yeah, I have my hand raised.
Okay, Milo, why did you go first? You started talking, and then
Yeah,
we'll go
okay,
to
good.
Veronica.
So you mentioned, you showed how by using the two stereos and SDO, probably the best configuration for those three spacecraft is when they are 120 degrees from each other. But I want to understand what happened when you don't have that ideal configuration. And we all know that one of the stereos stopped working several years ago. How your model tried to compensate for that, and what are the limitations on the spacecraft locations for these 3D models?
So there's an example that I could show this, for example, where we only use 2 viewpoints, which means that there's a part of the sun that you can't see, but you can still try to reconstruct a portion of it and extract information from it. So that's one of the challenges. The fact that we had 3 satellites positioned the way we were allowed us to do a full reconstruction. But if the separation angle is not right and there's a coverage or a part of the sun that's not covered, then obviously the model cannot reconstruct that part. But it can try to reconstruct the part that it does see. So you're not going to get a full sun, but you'll get a partial volume, essentially. And one example that I can show is, so have this as a backup. For example, we only use stereo A and SDO AIA, so 2 viewpoints. Not a lot of separation angle, but we can still try to make a reconstruction for that range that we have access to. And with this, we tried to, for example, reconstruct what solar orbiter should be seeing. So basically, the images that we were used for training are shown on the top. And we have at the bottom an example of the solar orbiter image that it captured at 304. And on the right, you have an example of basically our model reconstruction of what solar orbiter should be seeing. So you're going to be able to generate views for that range of angles that's covered by your input data. But if we were to look at the sun beyond that, there probably is nothing, or a very strange looking sun.
Yeah.
It's only valid for what's
Can you
covered.
generate a 3D image with a single viewpoint, or do you need at least 2? And if you need 2, what's the minimum angular distance between those 2?
Right. Trying to assess this is part of work that we're going to try to do in the near future, which is basically trying to measure ideally number of viewpoints that you need, separation angles that are required, and things like that. From one image, it would probably be very challenging. Two is we show that we can get something, like for example in this case. But these are all things that we'll have to really assess to have a clearer answer in terms of what's ideal.
Sure. Last idea, when you show the heights, it would be really cool to try to match that with this Parker spiral and see how that compares with the ballistic propagation of the PFSS models for the heliosphere. Just an idea.
Yeah, good idea. We'll take that into account. Thank you.
Great, thanks, Milo. Ronnie, do you want to go ahead?
Yes, very interesting talk. Thanks. I wanted to ask you, but actually with the answer to the previous question, you partially answered my question. So I was wondering if you intended to use the real solar EUI images when they would go over the pole in order to improve your model. But I see that you first will need to do the instrument-to-instrument translation before that. So is this something that you want to do, that if you are in contact with the EUI team at ROB, or, I mean, this would be, of course, a very interesting collaboration with our guest investigator program for EUI. If this is of interest of you to, in the future, use the image, the observation from the poles in order to improve your model.
Yeah, so absolutely. We're definitely interested in trying to use EUI images as a way of trying to make reconstructions, as well as trying to validate what we see, for example, closer to the poles, because that's one of the challenges that we get as we move to the real observations. We don't really have access to those images yet. So we can generate images from the poles, but we have nothing to validate against. So ideally, having images from higher latitudes would be great. And we are looking forward to using EUI images, but like is mentioned on this slide, we do need to develop the instrument translation for EUI images so we can make it work with our model. So for example, stereo was translated to SDO AIA-like images, and we would have to do the same thing for solar orbiter to be consistent.
Yeah, I don't know if Robert can comment on that. I guess he's in the audience.
Yeah, he should be in the room.
I mean, is it like, are they really different? I mean, it shouldn't be that difficult to translate AIA to EUI, FSI. Can you comment on that, Robert, or you haven't looked at this yet?
Yeah, I can comment on this. It should be pretty much straightforward. Of course, there are some differences in terms of the varying orbits and distance from the sun that we need to take care about. But other than that, it should be straightforward.
Yeah, you do have some time, of course, when solar orbiter is aligned. So Earth, solar orbiter, and Sun are aligned, and then AIA, they see the same thing as AIA. That happened like in March. I mean, there are some sequence of time where this is the case, and that it should be used for when you do this I2I.
Right. I mean, one advantage that we have with this method is that it doesn't require an overlap, so we don't need specifically an aligned data set. So it uses this unpaired image-to-image translation. So we can just translate between the individual instruments without having actual overlap. Well, some overlap is good, just for verification. So this is usually the way that this is done, is like, it's pretty much straightforward, just having two data sets available and translating between them. And then it's more about validating that the results that we have are consistent. So for this, we need the overlap and the pairing and see if this is all valid, what we get out in the end. But yeah, it's definitely on the plan, should be covered within the framework. Yeah, would be happy to work on this in the future.
Okay, thank you.
Thank you.
Great. Is there any final question from the audience or online?
Actually, we have one unanswered question in the chat.
Oh.
There's one place, yeah. Thank you, Benoit, for the talk. I think my
part of my question has been answered by the previous person that asked, which was I was interested to know about the translation because you mentioned that captured some images from different wavelengths. So I think your answer then is image translation, I guess.
Yeah, it is a component at the moment. If we were to look at a different approach where we would try to, say, incorporate for instrument response functions and things like that, then we might not necessarily need it. But at the moment, with the way we're working, yes. We're translating stereo images as well as, ideally, solar orbiter images in the future. We're all translating them to look like SDOAIA images. So it's all a consistent homogeneous data set.
Okay, all right. Thank you. Thank you very much.
Great. Awesome. Well, let's thank Benoit again for a really interesting talk.